Start? Good. Thank you for coming. This will be a joint session, Swisscom AVI Networks and Hewlett-Packard Enterprise. We are here to talk about our challenges in implementing the MediaCloud, the special, I would like to say a niche implementation of NFV in Swisscom environment. Before we start, this is our agenda for today. First, I will, from the Swisscom side, give just a high-level view on why we are here and what were the drivers. And then the gentleman on my left and right side will dive into the topic and explain how we did it. Let's start with Marco. If you can say what is your role, please.
Yeah, my name is Marco. I'm based in Switzerland. I work for Hewlett-Packard Enterprise in the media and entertainment domain as a solution architect, and I will dive into technical details of implementation, challenges, and what we did on OpenStack to make this work.
Ranga?
Thanks, Marco. My name is Ranga Rajgopalan. I'm CTO and co-founder at AVI Networks, and we have been working closely with Swisscom in delivering this highly elastic and available application.
My name is Misha. I'm working for Swisscom as a product owner of virtual headend. My role is bouncing between architecture, solution architecture, and the project management. And in this presentation, I'll be more focused on the challenges which we have in terms of project. I won't use too much time on that. I would like to give more time to Ranga and to Marco to explain the implementation details. The department I'm working for is the Swisscom TV Entertainment, and in past several years, Swisscom TV Entertainment department invested a huge amount of effort to find the right technology and right way where we were going to migrate our services. We are trying to generate the runaway for all our entertainment services, not just for streaming. And we had some, if I may say, unique challenges. I hope you can learn from them. They may be unique to streaming, but if you are tending to generate or to create a high-performance media cloud, I think you will find them useful. Before I jump into more details, very short, Switzerland is a small country. Swisscom is a market leader there. We have from 3.4 million households. We have 1.5 million customers on the TV. At the moment, that's the leading number in Switzerland on IPTV market. This is how our customers, our competitors sees us. High satisfaction level, product which we are offering on the market is well accepted, is really popular. There are some numbers about streaming, maybe interesting for you. We are recording all the channels in a cloud environment. We are talking about now environment of 90 petabytes. The recording started somewhere 2014. It's around 650, 700 unique channels which are being recorded. We are growing like 5 petabytes per year. It's fun fact, but I checked yesterday the CERN presentation, and we are not as large as them. I was under impression we have quite a large environment, and we are not there yet, but who knows. Lot of unicast streaming, mostly due to the usage of VODs, and so video on demand kind of service and everything. This is our way. I'll not spend too much time. There are 3 important points. We started implementing Media Room at 2005. We were on market 2006. I was one of the initial part of an initial team deploying this environment. We launched until 2012. We were running our, let me say, media room environment, and then we decided to take control back into our hands. We were migrating development and building development teams. So in 2014, you can see the picture on the left down corner. That's our set-top box based on Android, designed by Swisscom. Some unique services are being offered, and this is running on the Swisscom backend. 2018 is important. This is what we are focusing here in migrating some of the services already to the OpenStack cloud-based environment. before we jump in and show you the vision, just shortly spend 1 minute on how our legacy environment looks like. All these red arrows present a multicast. So we have some unique requirements, and let me say, if we are migrating to the cloud, we are talking about multicast inside the cloud. We are talking about high quality network, no packet loss. I mean, really no packet loss, 0 packet loss, measuring over 24, 48 hours. We are talking about legacy network where unicast and multicast traffic is completely separated. So we can't go just with Docker with a single network interface. So some of the challenges exist. We had to respect that. The reason to use a multicast, there are several of them. The components behind and before the cloud environment, they're all unicast producers and after that consumers. So we had to fit that into the system. This is where we are. So Swisscom Vision is a streaming platform which offer our vendors a fair environment where they can compete with their components in terms of price, quality, and flexibility and feature set. Why I'm saying that? Because some of these components are transcoders, probes. Let's say we already migrated that, but there is not a single vendor here which comes with their own ecosystem. So we ask from our vendors to deliver small components which are API driven. You can configure them, you can deploy them, you can manage them without any additional components. So each vendor who wants to work with us, it has to be on the partner relationship, not kind of supplier-customer relationship where they sell us something. We develop together this environment to make it run. This is our vision. What I want to say about this picture, what is important, what it tries to depict is that service orchestration is crucial for us in delivering end-to-end service in matter of minutes rather than months. We already have the first small cube-like picture, so depicting virtual headend is already productive and live. We have 150 channels up and running, and we are migrating the service until end of this year. We plan to have between 300 and 450 services. AVI network is already used in production, and there is a project running in the background to integrate the rest of the services using flexibility of AVI balancer. Going fast forward, and then I will give the word to Marco, is the challenges which we have. Obviously, such kind of project and with this magnitude had several layers of impact in my organization. We can talk about business impact, social impact, and technical. When we talk about business, I'm, as an engineer, I said that many times, absolutely excited about OpenStack and all the technologies, what we are doing. I would do that for free, absolutely, but it has to make a business case and reason for the rest of the organization. Before we started this project and got the funding, we had to prove that a case that deploying the channel, which is a service for us, will cost 30% less in a real world. And I can tell you this works out with every CPU technology works for us here. With every new CPU and new generation, we are better and we are achieving better and better density and better quality of the service. Some of the just mention one technology challenge, which is for me popping up as the most important. So when you start such a project, it's kind of almost on the edge of being scientific and research project. You typically know what you know, and you know what you don't know. But what you are in kind of 2 years period, you end up in the places where you could not predict that it will happen, like I don't know, this network card would not work with the multicast, or IGMP snooping is duplicating the channels, the streams and stuff like that. So we had to go through all these diseases. We have a running environment, and I will finish my presentation with stating just Swisscom has an open policy. Please come to me if you're interested, if you're coming even from the telco world or media side, if you're interested to go deeper into the topic and cooperate with us, just send an email. There is also QR code. I'm not sure if you have seen it with this presentation, and there is also our details, so please use it. Marco?
Yeah, thank you. All right, I go into a little bit technical details as well, but first I would like to ask who is connected to video and media at all in here? Okay, so not too many. Yeah, okay, yeah, there. So then before I go into more details, just what is a headend? A video headend is a part of a solution that is run by broadcasters and operators also in the media environment that does transcoding of video signals. So 80%, 70%, depending if you're an operator or broadcaster, of channels that you can watch, live channels on your whatever device, are either acquired from a satellite or the operator gets them from the studio. And what you do in the headend is transcoding them, bringing them into the format that you require. Right? That's quite a heavy lifting job. Latency is important, and quality is important as well. And it's a CPU-intensive job. So if you look at headends that are out there at media operators, they look simplified a bit like this here, right? So you have a video signal coming in, they get transcoded. You have a lot of different managers for different transcoders. So if you as an operator started 10 years ago to launch an IPTV services, you picked and choose the vendor for standard definition channels, right? So to do SD transcoding. A couple of years later, probably high definition. And then 1, 2 years later, or before high definition was OTT to offer streaming to mobile and web and whatsoever. Now 4K has been coming already, UHD channels, there is certain content already there, at least in Switzerland for Swisscom there is. Next, HDR and so on and so forth. So technologies are changing, and operators have been tending to choose different vendors for different use cases because of one vendor is better in high definition, another vendor is better for OTT, and so on and so forth. So you end up with such a situation where you have a complex environment of a headend of multiple different vendors of transcoders and multiplexers, and all with their own managers, and even different teams that operate those different things. Right? And migrating a channel from standard definition to high definition, or offering a new channel in OTT, is operationally quite a complex task. And it also produces a situation of some sort of vendor lock-in. Because if you have been deciding as an operator for a specific vendor to do high definition, you're running 100, 200, 300 channels on a cluster of appliances from this vendor. You're not going to launch your next channel on a completely different vendor because you would have to build a new cluster. Right? You cannot just buy one appliance and then put it into place there. What we did actually before we started this project, we were working on other NFV projects together. And after we've been putting into production a telco cloud for virtual CPE, we went to the TV department and said, well, hang on a second. We learned now a couple of things on how to make cloud and networks carrier grade. We think we could use some of the learnings also for live media processing. And that's what we then drawn as one of the slides as well. We went together with Swisscom, we went to the vendors of those applications. Those Ericsson's, Harmonic, TIM, and so on and so forth, and ask them for a software version of their transcoder or multiplexer, or what it would be. Or even a container version, or a virtual image, or whatsoever. And it needed to provide us with an open API so that we can control it. With the goal to have one, I call it one ring to rule them all, one management system, the virtual headend manager. That's a product that we've developed together with Swisscom, which is now an HP product in production. And this would be the one controlling system to get rid of all the other controllers that you would have. And when we started, nothing did exist. We were the first one to try to do something like this. There was no reference architecture, nothing. So we took, well, Etsy, right? So let's start with Etsy. Build, you know that if you know NFV, right? Standard infrastructure, put virtualization layer on top, and let OpenStack do the infrastructure orchestration. For Swisscom, it was important to have open interfaces on each layer. Right? So hardware should be replaceable, but also the cloud should provide open interfaces. We started the project with Helium OpenStack, which is in the history books now. And later on, we migrated that to Red Hat OpenStack together with Swisscom. And the migration was quite simple because of OpenStack. Right? So we just used standard OpenStack Nova APIs to manage our resources. On top of that, you would put your applications that you want to have could be transcoders, multiplexers, probes, as VNFs, right? Virtual machines in our case. I'll talk later about why virtual machines. And then, of course, you would put on top some service orchestration. So 2 major challenges we had. One of them was in the infrastructure layer as such in OpenStack to make it capable of running those multicast workloads. I'll come to that a bit later. The second one was the maturity of those VNFs that we would put on top of it. Right? So the broadcasting industry is a bit behind the telco industry in general when it comes to virtualization and open APIs and control. So when we were started talking to vendors that provided us with transcoders, we asked them, yeah, are you cloud ready? Do you have virtual appliances or containers whatsoever? And they all said, yeah, of course we are. But it turned out that they were not at all. Right? So the hardest part basically is get our partners that we onboard into those systems or into the virtual headend to get them from a decoupled state where they are running to run their application on standard hardware to a stage where they are cloudified, which means to control the whole life cycle of the application in a programmatic way. So if there are still user interfaces where you have to click around in order to configure something, that's not going to work in cloud, right? And if they come to us and say, yeah, we are virtualized, if this means that the application can be installed on a virtual machine somewhere on ESX, that's not cloud, right? So with every vendor we onboard, it takes us sometimes a year to get from virtualized to cloudified. And it's simple things like license models that have to adopt. If your license is bound to a MAC address, it's not going to work. Right? Another picture that we've drawn now more on the infrastructure side. So it seemed that we were some of the first people that tried to do multicast in a virtualized network probably. Or tried to do. No, the code was there, but nobody ever tested it before we started. So this is applicable, this slide, both to NFV workloads, but also headend workloads. I'm not going to go into too many details. Just like what you know, enhanced platform awareness is important. So we knew from the beginning that we would have to use probably NUMA awareness, NUMA pinning, and also that standard OVS is probably not going to work. So OVS is processing packets by using CPU power, and the application we run are also just pure CPU consumption, a transcoder. And they compete against each other. When we started, we tested on 10 gig network interface cards how much multicast traffic we could run through Open vSwitch before losing packets. And it was like 50 megabits per second. And that's not enough at all, of course, right? So OVS is not the most efficient virtual switch out there, but in multicast it's even worse, or it was at least even worse. So we were looking at tuning options that you would have also from NFV, right? So if it's really ugly, not really cloudy anymore, you could use PCI pass-through. But that's not what you would want to use if you want to use cloud principles. Second one would be SRIOV, also still less flexible than using OVS as a pure virtualized switch. So we were looking at NUMA pinning and TPDK, and that's what we actually use. Later on, we found out that SRIOV wouldn't even work. I mean, even though it gives you line rate with the NICs that we tested at this time, the virtualized function on the network interface cards that we tested at this time did not support IGMP. So it meant it did not support multicast. So if we would join a TV signal, it would just flood it to all the guests that were connected to it. Right? But DPDK did the trick for us. So we spent approximately a year in analyzing OVS. We got great help also from the OVS community. We had to change a bit the source code, especially the rules on how to treat packets in multicast traffic, push it upstream again. And since OVS 2.7, you can use it, and it will perfectly be able to handle multicast traffic. We are using containers in virtual machines and not running on bare metal. And I'll try to explain a bit why we are doing this. So we are getting transcoding applications that we run in production now are from a TEM and a Monic. If you work in media or business, you know those two vendors. They give that to us in containers. Main reason why is because everybody thinks containers are cool. And they are cool. Especially as a nice way of life-cycling applications. Right? If a way of packaging and shipping them and so on and so forth. If you get a new version, you just start a new container, and that's then it. However, we decided to put them into a virtual machine, and the main reason are networking concepts of Docker. Right? So a second thing is it gives you a little bit more hardware independence connected to the network, to the networking performance of Docker. So I'll come to that in the next slide, but fact is we cannot use for live media processing the network isolation of the Docker networking bridge. It doesn't work, it doesn't perform, it doesn't scale at all. So even after 20, 30 megabits per second, we start losing packets. So we need to run the containers in host mode. And if you do that, you basically lose the complete isolation from networking perspective, right, that Docker would give you. So we bridge the gap there by using virtual machines. And also an important point probably is that, I mean, cloud, especially OpenStack and virtualized systems are quite mature now. So they offer you a lot of tools and possibilities to do monitoring and management, which we thought when we started, at least in container world, were less advanced. Now this will change in the next, I hope, 1-2 years with Cube. But this was at this point in time. Drawbacks that you have is that you have an overhead of 5 to 10% probably with virtualization, and you need to manage an additional component, the guest operating system. But for us, it was the only way to get this productive at this point in time. Now, in Docker networking, if you work with Docker, that's not applicable for Kubernetes at all, but if you work in Docker, you know that actually there are 4.5, well, depicted here only 4, networking modes that you can start the container. So one is bridged mode, which is the standard mode, right? Using the network isolation of Docker, we cannot use that. We lose packets. We cannot have multiple network interfaces on our application, which we need. So if you run a transcoder, you have sometimes one interface where you have ingress traffic, another one where you have egress traffic, another interface where you have management. And we need to have this, right? So just the standard network bridge mode does not work for us. There's networking mode none. So of course, you can run your containers without any network connection. That's not applicable for us. We need this, right? Another one is the container, so neighbor container mode. So you could tell your Docker container when you started to use the networking information of any neighbor container. That's also not what we want. Actually, the only way to run currently live media processing applications is to run your containers in host mode, which means that it gets accessibility and full visibility to the MAC address and Ethernet interface information of your host. Right? If this is a bare metal host, again, you start your first container, it gets a MAC address and a couple of IP addresses. You start your second container, we'll have the same IP address, same MAC addresses. It's already not working anymore, right? Same with the applications that we get, they are not microservices, I think I said that before. Those are containers with multiple hundred megs or even gigs. And if you start such a container, they expose multiple services on many different ports. And so we needed this isolation of the virtual machine. This was really the main reason why we put Dockers into virtual machines. Multicast and OpenStack. I don't know, I didn't go into detail what multicast really is. In essence, it is a one-to-many protocol in networking. So you have a sender that sends a signal or packets in UDP to a group address, and then your clients or receivers can join this group address. And the sender is not aware of receivers. This also means that you can stream a TV signal, TV channel once, and you can have 1 million subscribers to it, and you only have once the traffic that you generate at data center level. This non-awareness between sender and receivers means that lost packets cannot be resent, because the sender does not know who was receiving them and what was lost in the way. It's shoot and forget for the sender. And this dictates actually a flawless virtual network. So as Misha said before, flawless means 0 packet loss. And the tests that we run were 48 hours without losing any packet by generating 2 times the bandwidth that we would need after our host was anyway saturated by CPU consumption. Right? And this was good enough then to go and to develop further. So if you look at OpenStack, we were looking at, we use OpenVSwitch as a virtual switch in OpenStack. And Multicast is not available. It's not enabled out of the box. There are 2 commands that you need to run on OVS control to enable multicast. The OVS supports IGMP snooping already, so that's good, but you need to enable it. And problem is Neutron layer 3 does not support multicast. So you cannot do layer 3 routing within a virtual network. So it does not route any multicast traffic. So the only way to really do multicast in an OpenStack or virtual network with OpenVSwitch is to use Neutron provider networks. Right? So you need to have your router outside of the virtual network. Routable public VLANs, as I said, gateway outside, and then attach Nova instances directly to provider networks. And PIM and routing, again, outside of it. That's actually already the trick. So if you know how to tune an OpenStack to be telco grade, use latest versions of OpenVSwitch and enable DPDK, it absolutely works now. It does not work with uncompressed streams yet,
Yep.
but if you have compressed inputs, actually that's absolutely good. So Misha said we're in production. Currently it's around 130 TV channels that are streamed to customers already. And this will be scaled at least doubled, if not tripled, I think, this year. And yeah, looking forward.
I just have a, yes, very small add-on. So the development, what we did on the OVS switch, that HP did with us, they're upstreamed and they're available in this version of OVS. So everything what we do open, we upstream, and we do not use the proprietary components. That was one of the requirements for Swisscom. Okay.
Ranga?
Oh. Thanks, Marco. So Misha talked about the overall vision and what Swisscom wanted to accomplish. And Marco followed that up with what were some of the data plane challenges. We will look at a slightly different topic. We will look at the control plane. And in this case, the control plane is really the user who flips a channel or sends the control down to the actual cable system. And these are sent through the set-top boxes. Now, unlike retail, where you can have huge spikes in traffic, you can also have similar situations in a more controlled environment. An example could be when a new software version is rolled out on a set-top box, or it's a scheduled maintenance of a set-top box. So you can have situations where you have a lot of incoming connections into the control plane. And these happen for short durations, and then they go away. So what you really need is something that adds a lot of elasticity to the overall applications, which is a common application that we all see amongst many applications. It's a common pattern. And a key part of that is something called the load balancer. So we may all be familiar with how load balancers are deployed today. RB Networks started its life about 4 years ago. When we started the company, we wanted to actually start with load balancers and then see how we could build them in a fundamentally a cloud-native way. This is a picture of a traditional load balancer. It's our clients connecting to applications. And these are usually monolithic pieces of functionality, either hardware or software. They had everything built into it. You would connect to a VM or you'd connect into a hardware appliance and you'd configure it. And it would be running maybe 100 or a few thousand applications. What we did is we disaggregated the load balancer into two key pieces. The first one was a controller, which is responsible for orchestrating the load balancer. It was also the API endpoint. And then the second part was the actual proxy itself. The proxy was just a piece of software. It was built with high performance in mind using techniques like DPDK. And the proxy itself could now be distributed to run across any environment. It could be running, for example, as a VM in Nova. It could be running as a load balancer on a bare metal server. It could also be running as a Docker container, for example, inside Kubernetes. And so together, the experience that you as a user will have is using, for example, Amazon's ELB or ALB, except that it gives you all the features and elasticity that you need to deploy applications. It works in any environment, your data center or any public cloud environment. Now, what does the controller do? A key part of the actual proxies themselves are that they sit in between your clients and your applications. So they see every bit of traffic that goes in. They see the latency, they see the performance, they see errors, they see everything. So they act as these giant filters that just constantly collect a lot of information about the application and the performance and the clients and who are coming. And then they filter out the not so interesting stuff and pass the interesting stuff on to the controller, which provides analytics. And we'll see some examples of that today. And the second key functionality that the controller provides is also orchestration. As an example, when you create a load balancing service in the controller. In OpenStack, for example, it talks to Nova, it creates a VM. It talks to Neutron, it plumbs the right network into that VM. It creates a second VM. It monitors the availability of these services. If a VM goes down, it creates a third VM. So essentially, it's an orchestrator, and also it's an API endpoint for all these services. And then the third function it also does is capacity management. So a single cluster can have a few hundred or a few thousand applications. So it's the controller that places these services across these virtual machines or across these proxies that are running in a distributed way across your network. And it monitors both the capacity of the load balancers themselves. It also monitors the capacity of your backend. So if your backend application instances are running out of capacity, now you have the ability to elastically and automatically add more instances, or vice versa, reduce the amount of throughput and capacity that you have. So together, they provide functions like load balancing, security functions like WAF, DOS prevention, blacklist, whitelist, rate limiting, lots of detailed analytics on application performance, infrastructure performance, and of course, management in terms of centrally managed API endpoint for all your services in your endpoint. A key question that often comes up is, how does it scale? It scales very well. All we need to do is add more CPUs and memory to the system, and you can scale this literally infinitely as long as it is available, the resources are available in your environment. So let me quickly show you. So this is an example of a service that's, excuse me. Yeah, so this is an example of environment that's currently running. It's a single service, and it's scaled out across about 20 or 30 different virtual machines. And it's currently handling about 750,000 connections per second. It gets even better. These are just not any connections per second. It's not wholly interesting if these are just TCP connections per second. These are actually SSL transactions. So each handshake here is a full SSL transaction. So that's about 250,000 users who are connecting and disconnecting in a second. Performance of this class would actually run into 7 figures or even 8 figures, for example, if you were to use hardware for this. This is only possible because this is built on commodity software running on commodity hardware, and you can elastically increase or decrease performance. All you really need to do is just say, I want more performance, either through an API, or the system can also do that for you, and it automatically increases or decreases performance for it. And the last bit that I wanted to touch on is also, we spoke about analytics, and this is, for example, the dashboard of a service. This shows how far the clients on an average are from the load balancer. If it is high, that means you need to locate or move your application closer to regions where the clients are. This is usually low because the load balancer is right next to the application. This is the actual application response time. So this is the time when your GET request hit the application instance when it actually started to respond. And this is actually a data transfer time. So each number here really corresponds to a specific component in your latency, and if any of them are out of bounds, that means different teams have to be involved to understand what's going wrong. And this is on an aggregate basis. It gets even better. You can actually look at every individual transaction, and you can actually see where this transaction came in from, who's the client, what's the user agent, where it got load balanced, what's the actual response that went in, and then the response time for each one. So this provides very granular information, also summarized information that you can use to build dashboards on. And we, as Misha mentioned, have been closely working with Swisscom to actually put this into production as part of the larger overall IPTV environment. And so it's something that is available today. That's all I had. Any questions?
Can you start the last slide? Yep.
Yeah. Okay.
Actually, that's it. We are happy to answer the questions. And guys, if you took the pictures, it's totally fine, absolutely, but you have a QR code. We already placed it on a Google Drive. Just download it. You have our contacts. Please come to us. You can shoot now the questions or later via email, phone calls.
Instagram.
Thank you, guys.
Thank you very much.